found that the commutator relation of Lx and Ly was IH cross Lz. So this directly tells you that the commutator relation is not zero. That means you cannot measure them simultaneously. Similarly, the other two relations, Ly and Lz, also gives you Lx, Lx, and the other one is Lz, Lx, and I also told you how to write down these relations. It's a very simple cyclic relations in one particular direction. Okay, you cannot randomly pick x and y and z. So it is x, y, and z. So you can have this kind of relation. So if you want to have Lx and Ly, so what you get is Lz. Ly and Lz is what you get is Lx, etc., etc. Now we know that all these relations are non-zero, so that means you will never be able to get these values simultaneously. You have to measure, if you want to get Lx, you have to independently measure it. You have to measure Ly, you have to independently measure it. Let's say you do an experiment to find out what is L and Lx. Okay, L and Lx can be measured simultaneously because the commutator relation of L square and Lx is zero. Similarly, L square and Ly was also zero, and L square and Lz was also zero. Let's say you start with the experiment. Okay, you want to find out the magnitude of the angular momentum and the x component of the angular momentum. That is possible. You can get it. So that means you have measured a state, quantum state, with its magnitude and its x component of the angular momentum. Now you do the second time a measurement to find out whether it is possible to measure the y component now, the magnitude and y component. Now remember, you already have the information about x component of the momentum and the magnitude. If you try to measure the y component now, what you lose is the x component value. You can measure the magnitude, still you can measure the magnitude, but with the second measurement, you will definitely do not know what is the value of x. You will lose that information with the second measurement. Okay. Similarly, the third measurement will also lose the other information like Lz. If you want to measure, then definitely that quantum state will have no information about x and y component. So the meaning, physical meaning of all these relations are whether you are able to measure these numbers or quantum numbers simultaneously or not. Okay. Okay. These equations can be schematically written in a form which we call as Venn diagram. I'm sure you know this Venn diagram. Okay, so we'll try to put all this information into one particular two-dimensional diagram. So it looks something like this. So I have a circle, so I will put a second concentric circle, and I have this as the center. This is a circle, okay, and so I'll draw a line like this. So I will write down Ly and Lz, and all this here, which is outside this Lx, Ly, and Lz, is L square. What does this tell you? Each point in this diagram is a quantum state. Okay, every point inside this circle is a quantum state. Whether it is lying inside the area of Lx or Ly or Lz or L square. It depends on whether you know what are the values of L and Lx or values of L and Ly. For example, if you have a state here, as I said, every point in this circle is a quantum state. Okay, let's say about this one. This corresponds to a quantum state with L square value and Lx, because it belongs to this L square circle, plus also it belongs to Lx, while you do not know what is the value of Ly, do not know values of Lz. That's what our relation tells me. That if you measure Lx, you do not know what is the value of Ly and Lz. Similarly, you can consider any value for that matter inside this one. So Lz or any point here will be a quantum state with L square and Lz. No information about x and y component of the angular momentum. While if you consider a state here, a point here, that means this is a state with the L square value or L magnitude. Okay, and this point here, the central point, is a point where everything is zero. Lx, Ly, and Lz is zero. Okay, so you can write this as Lx equal to Ly equal to L0 is zero. That means the eigenvalue of these components are zero. Okay, and this diagram has all the information about these relations. The point here will have L square value defined and Lx value defined. The point here will have L and Ly, and similarly Lz and L value will be defined in these three compartments. While these three compartments also belong to this L value. Okay? So you can simplify those relations into a very, very simple Venn diagram. You do not need to by heart these equations. Rather, you remember those Venn diagram and you can write those relations. Okay. Okay. Now, generally, what we do is we will write the commutator relation in terms of x, y, and z. That's the usual style. Okay. But in the case of a three-dimensional object, for example, this object is in a random direction or any direction which makes some angle theta with respect to the x-axis or y-axis or z-axis. So this x-y-z coordinate system will never give you that information in which direction this object is pointing. Okay. So what we do is, instead of writing these Cartesian coordinates x, y, and z, we write them in terms of spherical coordinates. So this system, which is our standard Cartesian coordinate system, will be converted into spherical coordinates. That means every component, that means every value of x, y, and z will be written in terms of the spherical coordinates. Okay, spherical coordinates will have the values r, theta, and phi. And how do we convert? We will assume a three-dimensional space. Okay, let's say three-dimensional space. I have x, I have y, and I have z. Okay, so I want to convert this into a spherical coordinate system. So I assume an object here, which is connected to the coordinate system with some r. Okay, that's a position vector. So r is already, we know, x square plus y square plus z square power half. Or r square is x square plus y square and z square. So how do we know this? So you just get the projection along this plane here, and correspondingly you get the projection here and the z component. Oops. Okay. So if you do this, then you definitely know exactly how to convert this xyz component of this object into a spherical coordinate system. You consider this as, or from z-axis it is theta, and from x-axis also you can have a reference which is phi. Okay. You can write this x. So this is my x now. Okay. This is my y and this is my z. So you can write x, y, z in terms of this theta and phi and r. Okay. So we are in three dimensions. Remember, we are in three dimensions. So I have certain angle with respect to this plane, xy plane, I have certain angle with respect to z axis. While if you write that in terms of x, y, z, you really do not know what is the orientation, except that you know the magnitude of the position vector. Okay, so that is why we convert that into a spherical coordinate system, where you can write x as, so what is this vector now? This one. This will be r sine theta. And if you want to get the value of x, this will be r sine theta cosine of phi. Okay. So this is r. So I get the component of this r along xy plane, which is given by r sine theta, and then I get the component along x-axis. So that is cos phi. So this will give you r sine theta cos phi. Is it correct? Yes. So similarly, you can write y as r sine theta sine phi. So r cos theta, r sine theta is this one, and then the sine theta. Okay. Similarly, the z coordinate will be simply the cosine of this angle along z axis. So it will be r cos theta, with r giving you the value in terms of x, y, z coordinates. So you can convert this Cartesian system into a spherical coordinate, or in turn you can convert, if you know the spherical coordinates, you can convert that into Cartesian coordinate system. Okay. For example, theta can be written as cosine of z divided by r. Okay. So this z divided by r is cosine inverse of z divided by r is x square plus y square plus z square per half. Okay, so you can know exactly where is this position vector by knowing the x, y, z coordinates. If you are given with the x, y, z coordinates, that means Cartesian coordinate system, you can really tell to what angle this protrudes or extends to z axis. Similarly, you can write down phi. Okay, what you do is you find y by x. So y by x is sine phi by cosine of phi. This gets cancelled, so it will give you tan of phi, implies phi is tan inverse y by x. So you are given with the x, y, z coordinates. You can actually tell where exactly is this point by knowing the angle phi and knowing the angle theta. And r, of course, r is what you are given, x square plus y square plus z square square root. So once you know these r, phi and theta, you almost know everything about this object in terms of the location. Okay. So if you know how to convert this x, y, z into the spherical coordinates, we should also able to write these operators, angular momentum operators, in terms of r, theta, phi. Because you could write this in terms of x, y, z, you should be able to write down the operators of angular momentum using theta, phi, and r. Okay, we'll directly write these relations, and I will upload that in the lecture note how to get these angular momentum operators. Okay. You please write down. This will be Lx is I h cross sine phi del by del theta plus cot theta cos phi del by del phi. Did you derive this during electromagnetism? Huh? Next semester. Okay, fine. Ly will be I h cross sine minus cosine cos phi del by del theta plus cot theta sine phi del by del theta, and Lg is minus I h cross del by del phi. Okay. We'll just use these relations. It's not that difficult to derive these Lx and Ly in terms of spherical coordinates, but let's discuss more about these operators rather than just spending time to derive. Okay. Oh. Now L, for example, this is a quite simpler equation. Okay. It is IH cross the first order derivative with respect to phi. What did our plot say? I have this, and this is actually in 3 dimension. So it is, the motion is in 3 dimension, and it is defined with the position vector r. And I said this has an phi. So obviously the angular momentum of this along z-axis, okay, so it is going around, and the angular momentum across the z-axis should only be a function of phi rather than other angles. Okay, so you can actually say that this is how it works out. So in this plane xy, actually it depends the angular momentum of this along z-axis. So it makes sense. Okay, and then we will discuss what is this IH cross telling. So this tells you the variation of the function assigned to this particle across this angle, or as a function of that angle, which gives you the z component of the moment. Okay, so I can erase this, right? Yeah. So I will keep this equation and we'll discuss this little bit more. Lg is minus IH cross del by del phi. Okay. Now we already have this relation L square, and the Lg is 0. That's the commutator relation we have. This tells me that I can measure the magnitude in any experiment. I can measure the magnitude of this angular momentum, and simultaneously it gives me the g component of the angular momentum. Similarly, the x and y component. Okay. So that means if you define a function, then I can operate this function using this operator, L operator. I can operate the same function using the z operator, and I will get the numbers for the total angular momentum and the z component of the angular momentum. Okay, this can be measured simultaneously. Tells you that you can have a function and you can operate that function with this operator and this operator together. Okay, so that means if you define a function, let's say some function psi L m, I'll tell you why I'm writing like this. This tells me that I can use the eigenvalue equation L square phi L m should give me some value Lm. Does that make sense? I use this function, and this is a single function, unique function, because I can measure these two together. So that means if you are given with a function, you can directly measure L and Lz. So that means I can write these kind of equations. I operate this L square operator on this function, and it should give me an eigenvalue corresponding to the angular momentum. Similarly, I can use the same function Lm. I can operate on Lz. This should also give me the eigenvalue corresponding to Lz. Okay, Lm. I'm in general considering a function. Okay. Now this is a unique function. Why? Because the commutator relation tells me that you can use this function, single function. You can determine the value of L. You can also determine value of Lz in one experiment. Similarly, you can write it for L square and Lx, or L square and Ly. You can write that equation. Okay. So these are some special functions, and I will write that as L and M. And it so happens that we always write like this: L square operating on phi will give you an eigenvalue which is equal to h square L times L plus 1. We will derive this. Okay. And LG operating on the phi LM is giving you MH cross. This is for all, or for L equal to 0, 1, 2, 3, and this eigenvalues are for M equal to plus L to minus L. So what does this tell me? I have a function, that means I have a state, quantum state, and I measure the angular momentum of that state. And this relation tells me that I can simultaneously measure one of the component of XYZ. Okay? And that means this state, quantum state, is a specially designed or specially defined state where I can get the information about the magnitude and the Z component together. I can individually write the eigenvalue equation for the magnitude and the Z component using that special function. We will define this special function like this. And this operation of this function on L square operator will give you eigenvalue of this magnitude of angular momentum. Operating the function with the LG will also give you the eigenvalue of that LZ operator. Okay, so that means these are the values of L magnitude, these are the values of LZ, that's Z component. Okay, these equations are valid at one experiment. If you try to measure the angular momentum of any particle, for example, in 3 dimension, that means you directly get the values of the magnitude of L plus a component along one of these axes. The next set of experiment, for example, if you do to measure the X component, again L square Lx is 0, that means you can measure L and Lx. If you try to do that, you will lose the information about LZ. Okay, so L square Lx, for example, is also 0. L square Ly is also 0. In the next experiment, if you try to define or measure the Y component, then you lose this information about X and Z. You will not know what is the component along X and Z. But these are true. That means you can define a single function such that you can get the information about the magnitude and the component. What does this tell you? This tells me that the angular momentum can only have certain discrete values. For various values of L, 1, 0, 1, 2, 3, you can have some values of orbital momentum. Okay, orbital angular momentum or angular momentum in general. So this tells me that L is H cross times L plus 1 has discrete values. While my classical physics told me that you can have all the values of angular momentum. Well, this is not true now. This L value can have only some discrete values depending on what value of small l takes. Okay, and LG is also MH cross, and for M going from plus L to minus L including 0. Okay, we will derive this. How do we get this eigenvalues and how do we get this eigenvalue of the Z component? Okay, what does this tell you? Let's say I do a measurement of angular momentum measurement, and I get the value something like this. L square is something like 30 H cross square, some number. Okay. From this, you should be able to know what is L. Okay, this will be, this implies L is 5, right? So you can have 30 h bar square, or L is root of 30 h bar for L as 5. For L4, what will be the L value? Square root of 4 times 5, it is 20 square root times h cross. For L equal to 3, this will be square root of 3 times 4 is 12, so 12 h cross, so on and so forth. There is absolutely no way you can have any value which is in between, like 15 square root h cross. You cannot have that. Or let's say 18 square root and h cross. You cannot have that. So that means you can have only discrete values of angular momentum. It is equivalent to saying that, if you remember, we define the energies of a particle in a box, right? So you had a non-zero E0, that's the ground state, or I'll write this as E1 for example. The next excited state was E2, which was 4 times E1. You never had 2 times E1, for example. You never had 3 times E1. You directly had 4 times E1. The next excited state will be 9 times E1. There was absolutely no way you can have 5 times E1 or 7 times E1. Here also, this form of this equation tells me that you will never have a situation where you have 7 h cross. The total angular momentum cannot be like this, because you will never be able to write L times L plus 1 square root as 7. You cannot write like that. Okay, you will not get L times L plus 1 as 7. So that means only discrete values are possible for the capital L. Okay, so let's continue. If at all I do this measurement where my square of the angular momentum gave me 30 h bar square, and this corresponds to small l 5, L equal to 5. So as I said, as soon as you measure the angular magnitude of the angular momentum, you immediately get the values of Lz also. Okay, so that means you should also get the values of Lz depending on what value of L. And as I said, this m, that integral multiple of h cross, can have the value from plus L to minus L. So this means I can have plus 5, plus 4, plus 3, plus 2, plus 1, and 0, and then minus 1, minus 2, minus 3, minus 4, minus 5. That's the meaning of it. For a given angular momentum value, magnitude of the angular momentum, this commutator relation directly tells me that it gives me immediately the z component, and z component has so many values. Because my relation eigenvalue equation tells me that the operator Lz operating on this special function gives me integral multiple of mh cross or mh cross, where m is from plus L to minus L. Okay, so that means these are 11 values. All these Lz has the total angular momentum equal to 30 h cross square, or L square equal to 30 h cross square. So that means I can say that a state which is measured, or a quantum state which is measured for angular momentum, if at all it gives you a value of L as square root of 30 times h bar, then this is having, or this will have 11 values of Lz. Okay, or if at all you do this for the lower values, for example, this is L equal to 5, I said, right? For L equal to 4, this will be 4 times y is 20 h cross. So this will have, I don't know how many, 9 values. Similarly, you can calculate. So that means for every value of L, you will get a 2L plus 1 degeneracy in terms of LG values. And each of these LG will have the same angular momentum L. Okay? So let's do it again. I know it is not that, it's not logical. What I said was the magnitude of the angular momentum and the Z component of the angular momentum can be got with a single experiment. Okay? So that means I have this equation, eigenvalue equation, which tells me that there is one special function. I can operate the total angular momentum operator on that function. I can also operate the Z component of the angular momentum on that particular function. And how do I write that in terms of equation? I write this eigenvalue equation. I operate this L square operator on the special function. It should give me some value, and again that function. And these values are eigenvalues of the total angular momentum. Similarly, as I said, this can give me the value of Z. I'll write the eigenvalue equation like this. Okay? And the eigenvalue of LZ operator gives me integral multiple of H cross, and where the integral multiples are from plus L to minus L. So that means for a given value of L, which is measured by experiment, you will have 2L plus 1 values of LZ. Okay? Let's say L equal to 0. This gives me the total angular momentum 0. So that means LZ should also be 0, right? Is it correct? If this is 0, L is 0. So that means 2L plus 1 values. That means LZ will have only one value. For L equal to 1, the L will be how much? 1 times 2 is root 2 times H cross. Okay? And LZ will have how many values? 2L plus 1. That means 3 values. So this will give me plus 1, 0, and minus 1. Okay? So for L equal to 2, this will be 2 times 3 is 6, root 6. Okay? So this will be root 6 H cross, and correspondingly LZ will have 2 means plus 2, plus 1, and 0, minus 1, and minus 2, totally 5 values. So similarly you can continue for the higher values of L. So you can write graphically, if at all your measurement gives you a, for this measurement, okay, so L square is 30 H bar square, or L is root of 30 times H bar, with L is 5, right? So this gives you a angular momentum L value. And I said, if you get this value for L, root 30 times H cross, it will have 2L plus 1 values of LG. Okay, so you can write, so this is capital L and this is my M, for example. Okay, this M. So I will have 0. So for L equal to 5, is it 5? Yes, 5. This will be, LG will be plus 5, 4, 3, 2, 1, 0, etc., etc. Okay? So you can write this 0, and you have 1, you have 2, you have 3, you have 4, you have 5. This is 1, 2, 3, 4, 5. And this is minus 1, minus 2, minus 3, minus 4, and minus 5. So that means it is 2L plus 1 fold degenerate. Okay? So this gives me a 2L plus 1 fold degenerate. This starts directly from simple commutator relation. L square and Lg is 0 means it is possible to measure simultaneously these two values. That means you are actually having a function phi Lm, or you can also have phi, for example. That means if you use this function, you can get the value of L. If you use this function, you can also get the z component of the angular momentum. Okay, the relations were written in terms of the eigenvalue equation as L square times that special function will give you some number. Those are eigenvalues for this one. Similarly, for Lg, you get the eigenvalues for Lg and this one. Okay, and just to distinguish between L square and Lg operator, I will write L and M. L and M here. The function is defined with the particular value of L and M. Okay. Of course, the eigenvalues are square root of or h bar square L times L plus 1, and here it is simply mh cross. What does this tell you? If you go and measure the angular momentum, and if you get a value 30 h bar square, square of the L as 30 h bar square, it is possible that you can measure the z component within these 11 values. Your measurement might lead you a Lg value which is 5h cross, mh cross, remember, okay, m is having all these values. So that means your simultaneous measurement of Lg can give you 5h cross, 4h cross, or 3, 2, 1, 0, minus 1, etc., etc. Only one value is possible, but from this you can have 11 values. If at all, let's say your measurement gives you 4h cross, okay? That means my capital L is root of 30 h bar, and Lg is 4h cross, okay? Then the function corresponding to that state is given by phi Lm. That means I will write this as phi, or phi Lm is, L is 5, so it is 5, 5, and 4. This is how it is written. Remember, I wrote down the phi, L, and M. These are the numbers, okay? And for a given value of L, you have so many values of Lg possible. But in one particular measurement, only one value is given to you as a result. So that means you will get L equal to 5 and maybe M equal to minus 3 in one set of experiments. Or maybe 4h cross as mg or m value. So the quantum state directly is written as phi Lm as the L value, provided your measurement was given as 30h cross or root of 30h cross. Okay, so this is a special wave function phi 4, and this function operated on L square gave you the angular momentum, and that function operating on Lg gave you the z component of the angular momentum. That's how the experiment goes on, and all that is originated from this commutator relation. So you can say that, okay, my experiment gave me let's say 6h cross, root of 6h cross, okay. If your measurement of angular momentum gave you root of 6h cross, this is L times L plus 1, that is 2 times 3. So L is 3 for you. The z component will have 2L plus 1 values possible. Okay, so that means 2L plus 1 values corresponds to 7 values possible. Okay, that is plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. L is 2. Okay, yeah, great. Nobody is speaking. Hey, sorry, sleeping. Okay. So L is 2 means 2L plus 1. So you will have 5 values. So this will be plus 2 plus 1, 0, minus 1 and minus 2. In any measurement, these 5 values are possible, but any one particular measurement might give you minus 2 value only. Okay. These are equally probable. Another measurement can give you plus 2 or something like that. Okay. The quantum state corresponding to these numbers will be given as phi Lm as, let's say, if it is this number, then phi 2 and 2. Okay. For this. Or for this, it will be phi 2 minus 2 comma minus 2. Okay. That's how the wave functions for all the or quantum state is defined in terms of L and M. Okay. As I said, the origin is L square and LZ operator commutator relation, and you can arrive at all these discrete values of L and M, and you can write these special wave functions. So what did we learn? We said because this relation is holding good, LZ equal to 0, what I get is the eigenvalue of L as h cross times or L square as L times L plus 1, and for LZ it is simply M h cross. This M depends on values of L. Sorry. Okay. L is 0, 1, 2, etc. and M is from plus L to minus L. And you already know that this will give you 2L plus 1 degeneracy. Okay, we'll put this result in a simple diagram. Classically, or classical physics tells you that the angular momentum should be continuous or is continuous. It can have any values. While just using that operators, you know that the angular momentum is discrete and corresponding to, or the component along any axis will also be discrete values. Okay, and for a given measurement, you know how many values of LG will be attained. So let's imagine you have a wheel like this. So I'm just combining it with the classical experiment. Let's have a wheel, and this wheel is arbitrary placed in space x, y, z. So that means you will know x, you will know y, you will know z coordinate of this wheel. This is a classical wheel. Okay. So x, y, z is known. So that means for that particular system, if you take the center as a coordinate or the reference, for this you will know x, y, z. Correspondingly, this will give me r, theta and phi. Okay. Now let's say this is actually having a angular momentum, and we know from classical physics that the angular momentum vector is perpendicular to the plane of this, just because L is r cross P. Yes. Okay. So that means the L is defined as a vector which is perpendicular to the plane of this wheel. This is simply classical. So I hope this is perpendicular to the plane of this wheel. Okay. So this is my L. How do we define a quantum state for this particular wheel which has a well-defined L and LZ? That's one question. Or you can have a reference z-axis, for example. Let's simply use this as my z-axis. Okay. You can put the same question in a different way, that what sort of motion I should give this to this wheel so that I have a consistent value of L and LZ. If I measure once, I should get a value of angular momentum as L and correspondingly z component as LZ. If you want to get that, what sort of motion I should give this to this wheel? Okay, and classical physics already tells you that this L actually precesses around this G axis so that the L is constant, and if the L is constant, Lg will also be constant. Okay, so the motion you have to give, or the rotation you have to give, is something like this. If this is G axis, that means I have this L. This is angular momentum. I'm not just I will not put this wheel now. Okay, I'll just put this L vector here. And from physics, classical physics, we know that this precesses around this G axis. In such a way that it can have all the values of L, so any value of L, but the G component is constant. Remember, the Z component of this one is the component along x-axis. So whatever the orientation of this L across this cone, the Z component is constant. So that means you have to give a precessing motion of this L vector along the Z axis so that you have a well-defined quantum state defined by L square and Lg. My question was very, very simple. I want to give certain motion, certain type of motion to this wheel, classical wheel, so that I have a constant value of L and constant value of Z. And you know from classical physics that if you precess this vector L around this Z axis, then that means L is a constant value whatever the time you measure, and Lg will also be a constant value. Lg is this vector here. This is my Lg, right? And classically it says that all the L values are possible. From this, you can have Lg, you can have Lg, you can have Lg, like that. All these values are possible. I just draw a few points in that. Okay, that's the system we had in the classical physics. If you use the rules of quantum mechanics for this wheel, what does it say? It says the angular momentum is discrete, and the Z component of the angular momentum is also discrete. While the classical physics said that it should have a continuous values of L. Okay. Let's try to plot this discrete values of L for a given system. Okay. I said for L equal to 5. Let's simplify that for L equal to 2, because I don't want to go on drawing this. What happens to L equal to 2 if you have? That means my measurement in fact is L square is h bar square L times L plus 1, or L is square root of, what is this, 2 plus 3 is 6 h cross. That's my measurement. Okay, and if you have this key situation, all my values of M will be so L equal to 2, then I will have 2L plus 1 values. That means it is plus 2, plus 1, 0, minus 1, and minus 2. For the Lg values, it will be plus 2 h cross, plus 1 h cross, 0. You can write this 0 h cross, minus 1 h bar, minus 2 h bar. These are the values you will get. You can go and do the same thing for L equal to 6, but you need to plot so many numbers. So I will reduce my effort or my burden to draw a lot of things. Okay, I'll just give L equal to 2. So the magnitude of the vector is 6, square root of 6 h cross, and I will have 5 values of Lg. While in the classical physics I said you can have all these values possible for Lg. So that means your cones were defined in every value of Z, so that you have a well-defined quantum state of L and Lg. While in this case of quantum mechanics, it says that